Hello there, Mr. Sutton here, bringing you the AB Calculus 4-9 Extra Practice Number 2 solutions on linearization. To find the linearization of this function at a equals 4, let's first start with the general formula. L of x equals f of a plus f prime of a times x minus a. And now for f of a, that's basically going to be plugging 4 into this function here. So 1 over the square root of 4, which is going to be 1/2 if we simplify it. And now for f prime of a, well, first we need to find f prime. F in general, I'm going to rewrite this function as x to the negative 1/2 power, just to make taking the derivative a little bit easier. And now f prime, that's going to be, using our power rule, 1/2 x to the negative 3/2. So now f prime of 4, I'm going to rewrite this in fractional radical form. This is going to be 1 over, well actually negative 1 over 2 times the square root of 4 cubed. Taking this step by step, square root of 4 is 2. Cube that, we've got 8 times 2 is 16. So this is negative 1 over 16. Plugging it all back into this formula, we have L of x equals 1/2 minus 1 over 16 times x minus 4. For this one, we want to approximate f of 0.1 for the ln of x plus 1 function using a tangent line at x equals 0. So let's start with linearization formula. We've got L of x equals f of a plus f prime of a times x minus a. F of a in this case just means ln of 0 plus 1, which is going to be ln of 1, which is just 0. And then for f prime, well, let's take f prime of x in general. That's going to be 1 over x plus 1. And then f prime of 0 is 1 over 0 plus 1, which is just going to be 1. Plugging it back in over here, we've got 0 plus 1 times x minus 0. And now we have to actually plug in 0.1. So I'm going to say f of 0.1 is approximately equal to all of this with 0.1 plugged in. So if you want to simplify that, this is just going to be 1 times 0.1, which is 0.1, plus 0. That doesn't change anything. So there's our final answer. For this one, I want to figure out f of pi plus 0.1, or at least approximate it, for the tangent function using a tangent line at x equals pi. So let's start with the linearization formula. L of x equals f of a plus f prime of a times x minus a. So f of a, that's going to be plugging the a value pi into the original formula. So that's going to be tan of pi. And tan of pi, that's the slope at 180 degrees. So that's going to be 0. And now we need to find f prime of x. That's going to be secant squared of x. F prime of 0, actually, f prime of pi then, is going to be secant squared of pi. Now, secant of pi, that's really 1 over cosine of pi. Cosine of pi is negative 1. 1 over that is still negative 1. But if I square negative 1, which this whole thing is doing, I get positive 1. Plugging it back in over here, we've got 0 plus 1 times x minus pi. And now to approximate f of pi plus 0.1, I have to plug pi plus 0.1 in for x here. So f of all this stuff is approximately equal to this expression with pi plus 0.1 plugged in for x. And if we do simplify this, the pi's are going to cancel. We've got 1 times 0.1, and plus 0 is not going to change anything. So that all comes out to 0.1. For this problem, we're trying to approximate the cube root of 108 using linearization at a convenient a value. So let's start with our linearization formula. That would be L of x equals f of a plus f prime of a times x minus a. And for my a value, my point of tangency, my launching off point, I want to pick something that's easy to take the cube root of so that I can actually plug it into this original cube root function. So I'm thinking a perfect cube that's close to 108, how about 125? That's something I could see myself taking the cube root of. So then f of 125 is going to come out to the cube root of 125, which is 5. And then for f prime, well, let me first write the f function. That's going to be x to the 1/3 power. So f prime is going to be 1/3 x to the negative 2/3. And then if I plug 125 into that, that's going to be 1/3 times the cube root of 125 squared. Cube root of 125 is going to be 5. Squaring that is 25. So this is going to be 1/75 then, because 3 times 25. Plugging it all back into the formula, we've got 5 plus 1/75 times x minus 125. And then to approximate the cube root of 108, I need to plug 108 into this linearization formula for x. And it's going to be approximately equal to all this stuff. So this is going to be, let's see here, negative 17. So this is 5 minus 17/75, which if we wanted to, we could rewrite this as 4 and 58/75. For this problem, the derivative of a function a is given by this a prime right here. And they're telling us a of 1.2 is 7.5. If a linear approximation to a of t at t equals 1.2 is used to estimate a of t, we want to know what t-value gives us an approximation of 15. So let's start by writing a formula for the approximation. We can say a of t in general is approximately equal to a of 1.2, which is 7.5, plus the derivative of a at 1.2 times t minus 1.2. So this is just a general formula for finding any value at any time, the approximation for a. But now we want this to specifically equal 15. And this is a calculator problem, so we're just going to set this stuff equal to 15 on our calculator. So let me show you how I did this on my calculator. Here I am in my y equals, and just to break this up into manageable pieces, I chose to put this a prime in as y1, so now I can just plug things into it without having to rewrite it over and over again. And in y2, I actually put the left side of this equation, 7.5 plus the derivative of 1.2, so I did alpha trace and then y1 of 1.2. And then I also threw in the parentheses, but now I'm not using t, right? I'm using x. So x minus 1.2, because that's the input variable on these graphing calculators. And then for the y3, I put the second half of my equation, the right side, 15. I basically want to see when the left and the right intersect as independent functions on a graph. And to make my life even easier, I'm going to deselect, press the equals here, and deselect y1, because I don't actually want to graph the derivative. I just want to graph these two sides of the equation. So now going back here, I need to pick a window too. So looking at my answer choices, because they didn't give me a window, but looking at my answer choices, it looks like my answer is going to fall somewhere between 0 and 3. So let's use that for my window. So let me do 0 to 3, and then zoom 0, zoom fit. Let's see where the horizontal line 15 and my a of t approximation function are going to equal each other. So there is a of t, or at least the approximation, the linear approximation for a of t. And that's going to cross 15 where? Somewhere over there between 1 and 2. Let me do second trace, and then option 5, intersect. And my spider's already pretty close to the intersection, so let's just press enter, enter, enter to get approximately 1.698. So there's my graph, there's my approximation, and that's going to be answer choice C. For this problem, they're saying that the locally linear approximation of the differentiable function f at x equals 2 is used to approximate f of 2.3. Approximation is going to be an underestimate. We want to know which of the following could have been the graph of f. So this is all about knowing what kind of functions a tangent line approximation will underestimate. And you might remember that a tangent line is going to underestimate a function that is concave up. But if you didn't, you could draw tangent lines at 2 for each of these functions. And if you do that, you'll see here in choice D, where the only one where it's concave up, your tangent line is going to be under the curve, which means that any values you approximate are actually going to fall short of the true value. So then we're going to go with choice D. On this one, they're telling us the line tangent to the graph of a twice differentiable function f at the point x equals 5 is used to estimate f of 5.25. Which statement guarantees our approximation at 5.25 is an overestimate of the true value? So with tangent lines, the whole over-under thing is all about concavity. So we can immediately eliminate choices A and B, which are just talking about whether the function is increasing or decreasing. It's not about that. It's all about concavity. So C and D we have to pick between. Which one's going to make us overestimate, if we're concave down or concave up? Well, if you're concave down, you've basically got like a frowny face kind of thing. So any line you draw on that is going to be overshooting the true value. So we're going to go with choice C. Concave down gives us overestimates.